Mr. Ibrahim, please, you can continue.
Then, yes, I think now it's okay. We can go through the immiscible displacement, actually. Immiscible means that the interfacial tension between, do you hear me?
Yes, we can hear you clearly.
Uh-huh. Means that the interfacial tension between two phases in the reservoir, that's water and oil, is greater than zero. What does it mean? It means that the most important to have the ratio, mobility ratio more than zero, because you need to have the flow of uh, of water, of oil, is easier and faster than the oil, so they don't mix together. That's why called immiscible. Thus, the two phases cannot mix molecularly. This is our mean. This is what they need. They don't mix, and so the process can go easier and as designed. Also, understanding immiscible displacement requires a knowledge of a frontal advanced theory. This can be found through the references of Dake, chapter 10, and Craig, chapter 3. That's reservoir engineering by Dake and Craig. Polymer flooding. Polymer flooding also have the same kind of is a project that requires some equipment. This is the basic of any project of any polymer flooding. The difference is that they have the same things, but they have a polymer solution from mixing plant. You have to have a polymer that should be suitable for your reservoir, and the polymer is mixed with water with certain percentage in order to be effective to push the oil to be produced by the production well, and not to mix with the and not to have fingering with the oil. And then followed that's as you see from this photo, that's the polymer solutions. That's number two. That's behind the oil and have to be pushed by driving water. So water here is used at the same time for injection. Description. Polymer augmented water flooding consists of adding water-soluble polymers to the water before it is injected into the reservoir. That's the job, that we need to mix the polymer with water and inject it into the injection well. Then, what is the mechanism that makes this that improve recovery efficiency? This is mobility control that improves volumetric sweep efficiency, and that's only one factor that makes the that's the main mechanism of the polymers to improve oil recovery. But as I said, polymer or any process have its own limitations. High oil viscosities require a higher polymer concentration, and another results are normally better if the polymer flood is started before the water-oil ratio becomes excessively high. We don't need to, we not to be late by applying the polymer flooding. So the best time is when the water-oil ratio not very high. Maybe you will have some water with the oil, but you don't need to have, you don't need, you should not leave the water oil ratio become excessively high. Also, one of the limitations is clays increase polymer adsorption. Uh, Clay is an eager, as I call it by myself, it's an eager kind of material inside the reservoir. It is very eager to absorb polymers. Also, some heterogeneity is acceptable, but avoid extensive fractures. If fractures are present, the cross-linked or gel polymer techniques may be applicable because it is when it becomes jelly, it cannot go through to the fractures or through the fractures very easy, so that we will not lose any kind of any material quantity of polymers. The challenges of the polymer flooding highlights is the lower injectivity than with water can adversely affect oil production rates in the early stages of the polymer fluid. The challenge is that it has a very lower injectivity than with water, can adversely affect oil production rates in the early stages of the polymer fluid. It's better be mixed with the certain percentage, not increasing or decreasing, it means that you have a limit of percentage of the polymers. Also, acrylamide type polymers lose viscosity due to shear degradation, salinity, and divalent ions. When you have salinity and divalent ions, the viscosity of the polymer degrades. Also, xanthan gum polymers cost more. As we know, the polymers are the most expensive material for in the world generally, and have a greater potential for well-bore plugging. It may cause also well-bore plugging, and this is another disadvantage of polymers. So you have to be careful about the quantity or the percentage of polymer in order not to arrive to such a problem. That's you're plugging the formation. Then we come to surfactant and polymer flooding. We have the same scheme of project, but we only have here is the polymer solution comes after the surfactant, which let's go from left right to left. First, you have oil. You inject surfactant, then you inject the polymer solution, and then you push by water, because this is the situation that's prevents the surfactants from degrades and do not do the job that's as it meant to be. A description of polymer or surfactant polymer flooding consists of injecting a slug, be careful, that contains water, surfactant, and electrolyte, that is salt, usually a co-solvent, alcohol, followed by polymer thickened water. You see, the component of such a fluid is very complicated. It contains water, surfactant, electrolyte, which is salt, and usually a co-solvent, that is alcohol, followed by polymer thickened water. And so that's why it is expensive and not preferred by the clients. So I said in the beginning, water injection and gas injection are the most dominant or most preferable usage or use of uh, enhanced oil recovery. The mechanism is that this mixture have interfacial tension reduction and improves displacement of sweep efficiency. Mobility control. You have to have a control on the mobility of the of this slug, which improves the volumetric sweep efficiency. This surfactant polymer process have limitations. An aerial sweep of more than 50% for water flood is desired. Aerial sweep of more than 50% for water flood is desired. That's the one of the limitations. So it requires a wider area and a wider fields in order to be effective. And limitations that it needs relatively homogeneous formations. Who can find a homogeneous formation in the globe? Maybe they are very rare to have homogeneous formations. Also, high amounts of anhydrite, gypsum, or clays are undesirable because they are very eager to swallow the slug, and only when it becomes gel, so that's swelling is the very low. Also, available systems provide optimum behavior within a narrow set of conditions. That means it's working not like the water injection. Here, the surfactant polymer work through conditions that's very strict, not so much, not so much preferable conditions of usage. Also, come with commercially available surfactants. Formation water chlorides should be less than 20,000 ppm, and divalent ions like calcium ion and magnesium ion should be less than 500 ppm. So that's that's what we said, the narrow set of conditions. We have to be careful about the concentration of these components. The chloride less than 20%, 20,000 ppm, and the calcium and magnesium ions should be less than 500 ppm. 500,000, sorry. The challenges, complex and expensive system. Since you are using such a number of components, then it's expensive. You are using alcohol, you are using surfactant. This makes the process is not likable by many contractors or many clients. Possibility of chromatographic separation of chemicals. There is a possibility that these chemicals separate, and each one goes to do the work by itself, not in combination with the other chemicals. Also, high absorption of surfactant. It needs more care to be careful. That requires surfactants more than the other operations. That if it is if surfactant work alone on the process. Also, interactions between surfactant and polymer happens very easy, or so because they are not compatible with each other. So that's why interactions happen. Degradation of chemicals at high temperatures. the temperatures of the wells are very high, and it requires it's just naturally because they are very deep or near the but they have higher temperatures than this at the surface, so these chemicals degrades during the injection of it into the reservoir that have more than 120 degrees C sometimes. That's I think this is the last one. The miscible gas flaring CO2 injection. We have the same sketch or scheme, but only you need CO2 injection from pipeline or recycle into to mix with the water or before the water, then followed by water. As you see from the scheme, that's the CO2 makes a front as a surfactant or miscible front, actually. Then followed by another by CO2, and then followed by or pushed by the water that have to be injected also uh, after this operation, of course. Uh, this description, CO2 flooding consists of injecting large quantities of CO2, 15% or more hydrocarbon per volumes, in the reservoir to form a miscible flood. The mechanisms that improve recovery efficiency: CO2 extracts the halide to intermediate components from the oil, and if the pressure is high enough, develops miscibility to displace oil from the reservoir. Please excuse me for a few minutes.
Wait, something is buried deep inside this hippo's eye. The oxpecker has to pull hard. Watch as it slow. Now it's hiding deep inside the hippo's ear. Watch the oxpecker reach inside, pull it free.
Excuse me, gentlemen, because I have to have water for my throat because I have a sour throat today. Thank you. As we said, this CO2 extracts the light to intermediate components from the oil. That makes which makes the that front between the CO2 and the oil in order to be in order to push, not to make a bank between the oil and CO2 in order to keep processing or to keep working on the oil. Also, the mechanism is the viscosity reduction of oil swelling. The oil, so this don't make a very high or a high viscosity oil. No, it reduces the viscosity of the oil. The limitations, that's very low viscosity of CO2, of course, as you know. It's a gas, results in poor mobility control, and the availability of CO2. You can't find CO2 available anyway, because the project is, this kind of projects are very expensive, so you don't find it too much. Also, the surface facilities of the project are very and much more than the others, and more expensive to the clients. Challenges is that we can have early breakthrough of CO2, which causes problems that you produce and lose the effect of CO2 on the project, and the corrosion in producing wells, because it's mixed with the water that you may find it within the oil. Or the oil or the water that follows the injection of CO2 makes a carbonate acid, which is one factor or more, one factor to make corrosion. Also, the necessity of separating CO2 from hydrocarbons and repressuring of CO2 for recycling. After production, the CO2 have to be separated from the mixture, and you have to have a pressurizing of CO2 again to be liquid in order to be recycled and re-injected into the wells. A larger requirements of CO2 per incremental barrel produced. In this process, you need more quantities of CO2 in order to produce the hydrocarbon that you may have in the well, which is mainly oil. Hydrocarbon injection, you may also inject any hydrocarbon gas into the well to enhance the recovery and improve the oil production quantities. Hydrocarbon, you see, these have the same scheme mainly, but includes, as you see on the left side of the scheme, that's hydrocarbon gas injection from pipeline or recycle. Also, you have some limitations. We will see that's the limitation of these factors or this description. We have hydrocarbon gas flooding consists of injecting light hydrocarbons through the reservoir to form a miscible flood. The mechanism that works on the trapped oil to increase the recovery efficiency. Viscosity reduction. oil swelling, condensing, or vaporizing gas drive. In this case, this fuel oil can be used to increase the viscosity of the oil, which is make it more easier than before to move and to be produced easily more than. The limitations of the hydrocarbon injection is the minimum depth is set by the pressure needed to maintain the generated miscibility. The required pressure ranges from about 1200 psi for the LPG process to 3000 5000 psi for the high pressure gas drive, depending on the oil. The challenges: viscous fingering results in poor vertical and horizontal sweep efficiency. Fingering is the main problem here, actually, or challenge, which makes a poor vertical and horizontal sweep efficiency. We may lose the process by making this horizontal or vertical sweep efficiency more difficult, or happens before the production of oil. Also, in this process, we need large quantities of expensive products solvent may be trapped and not recovered. It is a solvent, may be left. It may stay in the formation and cannot be recovered. So we have another problem better than we are solving a problem. Now we come to the thermal or steam flooding. It has a not very, but a more complicated surface equipment for this project. You need to have, as we go from left to right, a steam generator. We have water. We have injection well, reservoirs and separator to store the produced fluids, and we have a production well. The operation comes like this. If you go from left to right, that steam and condensed water are injected through the injection well. Hot water that's injected in the reservoir makes a bank, an oil bank. This bank is a mix of steam and oil. In order to prevent the mix or reduce the mix between oil and water, hot water. This process is most likely not required because of the, as we will see, that's the problem. Steam flooding consists of injecting about 80% quality steam to displace oil. It's not a very easy way to get 80% quality oil, steam, to be injected into the well that can work on displacing oil from the reservoir. Also, we have normal practice is to precede and accompany the steam drive by a cyclic steam stimulation of the producing wells, called huff and puff. This is an operation that's called huff and puff. Once for some time you inject steam through the injection well and produce it from the oil from the water from the producing well. On some other time, you have to, I repeat, make reverse the operation, makes the injection well to be a producer and the producing well to be an injector. And this operation have to be done through the life of the project so many times, depending on the reservoir and its characteristics. So need to be very careful about this one. Less companies use this kind of a process, actually. Mechanisms that improve recovery efficiency is that we are going to have viscosity reduction and steam distillation. In this case, that since we're having steam, that means very high temperatures. So this temperature reduce the viscosity of the oil and make it more easier to produce. Thermal expansion, because you have here a steam with high temperatures. This makes the other side, the oil, to be less viscous, and makes the other side, that makes the oil to expand by itself. So the production here would depend on two factors. The third one supplies pressure to drive oil to the producing well. Also, as we said, the use of water makes it easier to then using other components and other processes, because it gives the production of oil or the efficiency more easier, and makes the other side, the oil, to expand. Here temperature, but in oil, in water flooding or water injection, gives the pressure to the reservoir to produce. Limitations of the thermoplastic applicable to viscous oils in massive high permeability sandstones or unconsolidated sands. That's why it's used and mainly used use of the thermal is the high viscosity oil applicable to viscous oils and massive. It decreases the viscosity and increase the mobility of the oil to make it and make the expansion of the oil also. Also, high permeability. We need high permeability formation, and mainly sandstone, because high, as you know, that's heavy oil. Most prefer sandstone formations or unconsolidated sand. Also, one of the limitations is oil saturation must be high and pay zone should be greater than 20 feet thick to minimize heat loss to adjacent formations. In this case, when we inject the steam, we don't want to lose the temperature. We want to lose the steam to the other formations, or maybe lost in the formation itself. So they prefer here it is that we have a greater than 20 feet thick, because when it is thin, it will dissipate to the other formations, and then we lose the job, we lose the activity of the of the steam and its temperature. Also, one of the limitations that steam-flooded reservoirs should be as shallow as possible because of excessive wellbore heat loss. This is another, as we maybe described in the others, that's we don't need to lose the steam temperature to the other formations. That's why we need shallow wells in order that we can have less time for the steam to reach the mint oil. More limitations is the steam flood is not normally done in carbonate reservoirs because they're afraid of making another acids. That's the mix of steam with the carbonates makes they produce carbon acids, carbonate acids. Since about 1/3 of the additional oil recovered is consumed to generate the required steam, the cost per incremental barrel of oil is high because what we produce is very high viscosity oil or thick oil that will be used to generate steam. So that's the project is and the operation is very expensive. Low percentage of water-sensitive clays is desired for good injectivity because as we said before, the clays are very eager to swell any fluids in the formation. That's and of course there are some preferable. Water is most of the preferable, and steam, which is the source of it, is water. It becomes more eager to swell the water. Challenges: adverse mobility ratio and channeling of steam. We may have in this case, we have a mobility ratio of the steam is more than the mobility of the oil or thick oil or viscous oil. Any kind of oil is not required in this job. Here are some summary of screening. We have here the water flood. Required gravity is no, sorry, just a minute. This water flood formation type. If we have sandstone or carbonate, net thickness not applicable or not requirement. Average permeability any, depth any, and temperature any. For gas injection methods, we usually use in the hydrocarbon flood, sandstone or carbonate. The gas injection hydrocarbon, that's hydrocarbon gases, not and the formation net thickness is thin, less dipping. The dip of the formation is very thin. Average permeability is not mentioned or not required. The depth is more than 5,000 high pressure gas, and the temperature of the formation is not a problem or not mentioned. In case of nitrogen flue gas, preferable is sandstone or carbonate, thin and less dipping. Average permeability not mentioned, and the depth is more than 4,500 feet, and the temperature is not a problem or not one of the required characteristics. Carbon dioxide, sandstone is the preferable, or carbonate is the preferable formation type. Net thickness, thin and less dipping. Also, average permeability is not mentioned or not a characteristic. The depth is more than 2,000 feet. That's the minimum, actually, and not no characteristics of this one. A surfactant polymer, sandstone is preferred, and the net thickness more than 10 feet. The average permeability more than 20 millidarcy. Depth is less than 8,000. And the temperature is less than 175 degree F. Polymer formation type sandstone preferred, carbonate possible. No characteristics about this. Net thickness is not a factor. Average permeability greater than 10 millidarcy, normally 10 millidarcy. Depth less than 9,000 feet. Temperature is less than 200. And so on for the others. This is in case of chemical flooding. Polymers, alkaline, sandstone preferred. Net thickness not any or not required. And average permeability is greater than 20 or greater. The depth is less than 9,000 feet. Temperature is less than 200 degrees F. For thermal combustion, sand or sandstone with high porosity is required or preferred, greater than 10 feet thickness, and the viscosity of permeability greater than 10 millidarcy, and the depth is greater than 500 feet, and 150 degree F is preferred. For steam flooding, sand or sandstone with high porosity, greater than 20 feet thickness, greater than 200 millidarcy, and the depth is between 300 to 5,000 feet. The temperature is not a character. That's the end. Thank you. Any questions? Valerie, do you hear me?
Please, if you have any questions, just you can write it in the chat, or you can open your microphone and make the question to Mr. Ibrahim.
Yes, dear attendants, I'm listening.
Okay, I think like everything was clear for our attendees.
I hope so.
And yeah, I think it was really clear. Anyway, we have more questions. You can send the question to Oil and Gas, to Mega Plus Oil and Gas, and we can contact you with Mr. Ibrahim.
Just one last comment I want to
Yes, yes, please.
dear gentlemen and ladies, I have put this short webinar in order to make it clear for you what kind of operations we may have for extracting more oil from the reservoirs. But the details, you will find them in the main course. You are welcome to ask me anything during my email or through Valerie or through the anybody else.
Yeah, actually, we have a
Valerie.
question from Malzam. It says, can a well operate from the beginning to the end without having to adopt EOR?
Sorry, I didn't understand what he mean by his question.
I don't know if Malzam can open the microphone and make the question.
Hello, am I audible?
Welcome.
My question is, having understood that this EOR is like a modern method of how to enhance the recovery of our oil in our reservoirs. So, can these reservoirs function without having to adopt EOR, or it's something that is indispensable?
Yes, I understand your point, my dear. First, I said at the beginning, you have 3 stages of production. The first stage is the primary, that's done by the energy of the reservoir itself, either water drive, gas drive, gas cap drive, gas in solution. These 4 drives makes the production from any reservoir, but you can't find in the nature, you can't find a reservoir working on just only one of these drives, these 4 drives. So you have to be more careful that you have 4 drives, and you have to apply reservoir management. Reservoir management after simulation will tell you how much you can produce from this reservoir and what is the required production rate. You should not overcome this rate, because any increase in rate more than required, more than the ability of the reservoir, will destroy your formation, will destroy the energy of the reservoir, and will destroy and you will lose the quantity of a quantity of oil or hydrocarbon left in the reservoir, and you cannot produce it with the natural way. So you have to apply an improved operation or improved way of production, that's either gas lift or gas injection, and this is called the IF or ESP, to produce more oil. But then also you will arrive to a certain point that you will get water greater than oil. So you need to apply, in this case, you need to apply the EOR to extract the leftover hydrocarbon in the reservoir. Am I clear?
Yes, it's clear. Thank you very much for the answer.
Thank you.
We have one more question. I don't know if you can read it in the chat section. It says, in a mature shale sandstone formation, which effective enhance could be applied after secondary recovery has fully used?
Well, secondary recovery, EOR, is the last way of getting most of the trapped oil or in the reservoir or the yes, this is the last way, and up to now, this is the last way. EOR, you have to find out which is the suitable process for your reservoir and for your kind of oil, for your kind of formation you have. So this is the last frontier actually for the time being. Yes.
Okay, I think that was our last question. And I think with that, we can close our webinar. Thank you, Mr. Ibrahim, for all your presentation, for also answering the questions here with the attendees. We really appreciate. And I don't know if the attendees don't have other question, then that will be it. Thank you so much to everybody for being here with us today. Hope to see you soon. Have a good
Thank
day.
you. Thank you. Thank you very much. Bye bye.
Bye bye.
Thank you.